So thank you very much for everyone coming here today. So then this is our second session of the course. I'm very excited for today's session because we are going to see how everything really works in practice. And so today I planned to show you the most common techniques used for active learning and for selecting the most informative and the most useful examples for human annotation. And I'm going to focus, as I said in the last session, that I'm going to focus on uncertainty sampling because those are the most traditional techniques, and they are the techniques that are used more frequently in most of the cases. Okay, so next session we are going to see a little bit about user interface, active learning evaluation, and then we will have a hands-on activity. Okay, so let's get started. But before we get started, I would like to start with recap from the previous session. So then we saw in the last session that the difference between active learning and passive learning. So then in passive learning, so then we have a pool of labeled, a set of labeled data, right? And then we pre-process this data and we use a model for learn from this data for classification in future unseen data, right? So then this is how that works. And after that, what we have is we evaluate this model, right? And then if this model is, if we see that the performance of this model is sufficient for our use case, for our problem, then we deploy the model, right? So then this is the what we call passive learning, or the most traditional workflow of a machine learning process. But in some cases, we don't have enough labeled data, right? So then in this case, we have a small data set with labeled data. And then, but then the model performance is not sufficient for predicting, for correctly predicting from a pool of unlabeled data. So then in this case, what we do is we select the most informative instances from a pool of unlabeled data, and then we ask the help of a human, right, for this case. But for us to select the most informative instances from this unlabeled pool of unlabeled data, we need a strategy, right? So then this is what I'm going to see. We are going to see today. We are going to talk about the strategies used for us to select the most informative instances from this pool of unlabeled data, and then this strategy is going to be used for human annotation. So then it's going to be so then a user or an expert will have these most informative instances, and then this user is going to add labels to these instances, and then after that, these instances will be sent back to the algorithm, and then the model will be retrained. And then this loop continues until we get a performance, our goal performance. And then we assume that with this most informative selecting the most informative instances from this pool of unlabeled data, we are going to save time and also human effort. So this is the main workflow that we saw in the last session. And also we saw that we have two types of active learning architectures, the stream-based, in which the strategy is going to decide individually for each of them, the instances presented. So then it obtains a score of level of utility of each instance one at a time. In the pool-based, we rank order the entire collection of unlabeled data before selecting the best query. So this is the main difference. While in the stream-based, we decide the level of utility of each instance individually. In the pool-based architecture, we rank order a pool of unlabeled data before selecting, right? In terms of utility. So let's see the most useful strategies. So then the question is how to sample the right instances to be labeled by humans, right? We need to select, as I said, we need to select the most informative or the right instances to be labeled by humans, because this way we are saving time and also we are saving human effort. Consequently, we are reducing costs. So in the literature, we see at least 5 strategies, and those are the strategies that are the most frequent strategies used in the literature. We are going to see one by one, and they usually apply to most of the problems, and they are also used with all types of machine learning models, right? So then let's get started. So then uncertainty sampling. So then let's consider the following scenario. You gather loads of product review texts pulled from the web, and then you need to to carry out a sentiment analysis on this product review. So then you have to classify these reviews as positive, negative, or neutral. And then you train a classifier to evaluate your model on a set of unlabeled data. And of course that you are going to get, for each instance, predicted at least three probabilities, right? So then one probability associated with the positive, one probability associated with the negative, and one probability associated with the neutral class. So then, for instance, in this example, so then we have positive, negative, and neutral, but then the highest probability is 0.747, right? So then, of course, the model is going to be classified, this example will be classified as a negative because this is the highest probability, right? So same here. We have the highest probability as 0.5, but then we notice that this probability is the highest, but at the same time, it's very close to a decision boundary. As you know, for probability models, we usually a class is selected if it is above a certain decision boundary, which is usually 0.5, or below this decision boundary. So here we have two probabilities below the decision boundary, and then this one is high above the decision boundary, but it's still very close to the decision boundary. So this means that we assume that this means that the model is not so certain of this class, right? But of course, the model will need to select a class, but it's not so certain of this class. In this case, we consider this probability as the most uncertain is very uncertain. It means that the model is not so certain of this its decision. So then, how to calculate this? Usually, we can, of course, just select the probabilities that are very close to the decision boundary. But then usually what we do is we subtract 100%, we subtract 100% confidence, which is 1.0, from the highest probability. In the first case, it was 0.747. In the second case, it was 0.51. So then the result of this subtraction, we can assume is if it is close to the decision boundary, which is in this case here 0.488, we consider this as a good example, because this means that the model is very uncertain of this decision. When the uncertainty is low, as in this case here, we don't consider this as a good example, because this means that the probability is very high, and that probably the model prediction is correct, right? But then in the book Human in the Loop Machine Learning, the author he presents a way to normalize these scores. So then in this book, he presents a strategy for normalization of the least confidence, which involves subtracting the highest probability from 1, as we just saw, and multiply this result by the number of labels and divide by the number of labels minus 1. So here is the formula here. So then here in this example, so then we have 3 predictions, right? 3 probabilities associated with each prediction. Those are the highest probabilities for each of the examples. So then in the first example, the highest probability is 0.47. In the second is 0.11. In the third is 0.856. So then we subtract the 100% probability. This probability from 100% probabilities multiplied by 3 divided by 3 minus 1. So then we get those scores here. If we sort those scores, we can see that the example number 2 is the most uncertain one, because it gets the highest score of all, right? The number 1 is the second. The number 1 is the second highest, and the number 3 is the third highest score. So this is a way to associate a score in terms of utility, or in terms of informativeness to each of the examples. Okay, so the closer to 1, that means the greater the uncertainty. So as we can see here, the probability that is very close to the decision boundary is the one that gets the highest score, meaning that is the highest uncertainty score. Okay. Any questions so far? Is everything clear? Yeah. Okay, so then I go now for the...
I can ask a question, Natalia,
yes.
if you can hear me. So my question is, uncertainty sampling is one of the strategies for selecting the data we want to use in active learning. I didn't get exactly what is the terms of uncertainty sampling.
Yeah, it is. Uncertainty sampling is the strategy used for you to select the most useful or the most informative instances from a pool of unlabeled data. Okay.
Yeah.
From this pool of unlabeled data, you have to select the most informative or the most useful instances, because this way you are trying to reduce human effort and also to save time, because if you select randomly from the pool, the probability to get examples that do not contribute to the performance of the model is higher. So then what we do here is to select the instances that are contributing to increase the performance of the model faster. Did I answer your question?
Yeah, it makes sense. So that means in the sorted scores you have in here, the first one is which is the second example.
Exactly.
That means it is the most informative data, isn't it?
Exactly. Yes. Exactly. Yes.
Because it has
it has
lowest probability.
Exactly. Yes. So then it has the probability, not the lowest probability, but the probability that is very close to a decision boundary.
Mm-hmm.
The decision boundary, as we saw here, is 0.5 usually, right, for probability models. And if it is very close to the decision boundary, that means that it could be the model is not so certain. Mm-hmm. It's different here. This is above a decision boundary, and it's closer to 100% sure that this is the class.
I guess right? So the data that they are kind of the vague, we exclude them and bring them to the people to label them.
Yes, we are the data that is not so informative. Mm-hmm. They are not excluded from the active learning system, but actually they go to the bottom of the pool because they are not so important. Mm-hmm. Gotcha. Because they are redundant examples. They are not so. Actually, we assume, right? This is a hypothesis. We assume that they are not so important because the model already knows how to classify that instance. Mm-hmm. So then we select the instances that the models are not so certain of, and then we present that to the human. So then human is going to help the system to decide which class that instance belongs to.
Mm-hmm. Very good, thank you.
Okay, thanks. So this is one of the strategies. Next is margin of confidence. Margin of confidence is very intuitive because it answers the question: and how much more confident was the model then for a certain class than it is for the next most confident label or most confident class. So then in this example here, so then we have positive 0.2, negative 0.74, neutral 0.000. We see here that the model is going to classify the review as negative, right? But then the second one most confident label is positive. So then the model could be between positive and negative, right? So then we subtract this probability negative from positive, and then the result of this subtraction we subtract from 100% or 1.0. So then we get the scores here. So the lower the score, the higher the uncertainty. Does that make sense for you? If it makes sense, if it doesn't make sense, I can try to explain again. Okay, so the yes. Okay, so then the lowest the score, the highest the uncertainty, right? So in this case, usually we don't just, this is the final score, and then we do as we do here with least confidence. Then we sort the scores, right? So you can sort here the scores as well. So then we sort in.
Sorry, Natalia. Yeah.
Yes.
Can I just a question there on the number one, the 0.4211. Where did that figure? Where does that come from?
What?
No, the 0.4211. Yeah, that number.
0.4211. Oh, these now those are just examples. This does not come from. I'm just. Those are examples that I'm giving here as probabilities of
yeah, sorry. I see it on the former slide. Apologies. Never mind.
Yes.
Not good.
Yes.
Thank you.
This comes from yeah.
Okay.
Okay. So this is a second example. Okay. 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 This comes from the previous slide. Previous slide. Let me see. No, I think there is. Sorry, guys. I think that there was a mistake here. Actually, it should be subtracted 0.47 from 0.232. Okay, sorry, my bad here. You're right.
You did flash a slide there for a second, and I saw that 0.42 somewhere.
Okay. Yeah, but actually, my bad. Actually, it should be 0.2320. Okay.
Yeah.
So then we subtract this from this. Okay, negative from positive. Okay, and then we get a score. In the previous slide, we subtract the 0.112 from 0.132. Okay, and then the lower the score, the higher the uncertainty. Is that clear now? Yeah. Okay, so then next. This is margin of confidence sampling, okay? And then ratio. The ratio is very similar to the margin of confidence. So here, please ignore again 0.211, and then it's because it's 0.23. So then what we do is just to divide one by the other. Right? So then margin of confidence with subtraction does not differ from ratio confidence. Okay, so then those are two very, very similar strategies. But what we can see here is that the higher the ratio score, the higher the uncertainty. Okay? And as in all the other strategies, we just rank order by this score here in the first example, in the second example. Okay. Entropy sampling. The entropy sampling is a little bit more complicated because we have to understand the concept, the entropy concept. So the entropy means that the infrequent examples are the ones with higher amounts of information. So low probability event has a high information, surprising. The infrequent events are the most surprising ones, right? And then consequently, they are the events that have higher entropy scores. Examples with low information or unsurprising examples or frequent examples, they are the ones with low entropy scores. So rare events are more uncertain or more surprising and thus require more information to represent than common events. So this is the main concept involving entropy. Does that make sense for you? Any question about entropy? No? Okay. So very simple example. So then if we toss a coin and then we get tails, heads, heads, tails. So then next we don't know if we are going to get heads or tails. So then this means that we have a higher entropy because the level of surprising is high, right? The level of surprise is high. But then if you only get tails, 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 then this event has a low entropy because the surprise, the level of surprise is not so high. That's why we get this event usually has a low entropy. Okay, but how to calculate the entropy? Usually in the literature, the entropy is calculated and entropy is presented in terms of binary digits. And we use them traditionally, the entropy is calculated using the base 2 logarithm. And then it's a very simple calculation. What we do is we get the probability of an event, and then we multiply this probability by the log base 2 of the same probability, and then we get a score, the probability score. And then if we need to we need positive scores, we just subtract from 0. So then we get here, for instance, for a coin, the probability of 0.5 is minus 0.5. And for dice, which is a probability of 1 outcome between 6 outcomes, right? And then this is the entropy, 0.431. Is that okay so far? So far, so good? Yes? Okay, great. And now, query by committee. The query by committee is a type of strategy that can be used both for an ensemble of models, right? Also for just one model, for probability models, and models that do not return probabilities. For example, support vector machines, they do not return probabilities associated with their predictions, but they return the distance from the hyperplane, right? So then the query by committee is a strategy that can be used for models that do not return probability scores. So let's see. So then the query by committee, as I said, involves an ensemble of models, but then can also be used with just one model, one type of machine learning algorithm. If you use only one type of machine learning algorithm with this strategy, this involves training a model several times and look at the agreement on the unlabeled data across the predictions from each model trained. So this is how we calculate the query by committee. I'm going to show examples next. We can also use different models, and we can also calculate the agreement between the predictions of different models, or agreement between the predictions of several runs of one model. Is that clear? Yeah, okay, I go next. So what we can do is we can, for calculating the query by committee, we can retrain models with different subsets of items or different features. This is one way of calculating running the query by committee strategy. Or you can select examples whose levels of disagreement between the models is high. right? So let's say you have two models, and then the models that they have different predictions for one example. But for the second example, they have the same, very similar predictions, or actually equal predictions. So then you can calculate the level of agreement for each of the predictions of different models, okay? But for you to calculate agreement or disagreement between the models, there are also different strategies. You can use an agreement measure, for instance, Cohen-Kappa. This is Cohen-Kappa we usually use when we need to calculate the agreements between two models or two raters, right? Or we can also use the Krippendorff alpha coefficient for multiple models or multiple raters. Another way is to calculate the probability over the final classes assigned to examples by multiple models, right? So then this is very used for models that are not probability models, especially for support vector machines. So then we use different, we run different, we run different rounds of the same models to calculate, to predict, right? To predict classes from a set of unlabeled data. So then we run this many times, and then we calculate the agreement between these several runs, prediction runs of the same model. This can also be done with different models. So let's see here a strategy. So then for models that involves probabilities, for example, for multi-class problems which involves many classes, and the model needs to select one class from I don't know, 3 classes or 4 classes, as in the example that I showed for the sentiment analysis, neuter, positive, and negative. So in this case, we have probabilities associated with each of them. Okay, Connor is asking a question.
Hi, thanks, Natalia. When you were saying there, query by committee, is that to select the data that you should manually then go in and label for a human before retraining the model? Is that why you would select the highest differences?
Yeah, this is, as I said, this is another strategy, right? So then This is a strategy to select the most informative instances from the pool of unlabeled data.
And most informative in the sense of labeling for retraining by humans.
Exactly.
Or annotating. Yes. Great, thanks a million, thank you.
Exactly, yes.
Thanks.
Yes. Okay, so then let's say that you have 3 models, and these 3 models, they have different predictions for different instances, right? And then for instance number 1, let's say instance number 1. And then what we do is we are going to average the probabilities of these 3 models, okay? So then if we have 3 models with probabilities 0.5, then your average will be 0.5, right? And then after calculating these average probabilities, you calculate the entropy associated with each instance, as I showed it before. And after that, so then we are going to get one entropy score associated with each instance, in this case. And then we are going to have a pool of like a data set with instances, with the number of instances and then the entropy score associated with each instance. And then we can rank order this collection of entropy scores. After that, you are going to select from the pool the highest, the instances with the highest entropy score associated with it for human annotation. And after human annotation, you are going to send this labeled data, this set of newly labeled data to the model for retraining. Does that make sense? Okay. For the query by committee, for a multi-label problem. A multi-label problem, as you know, is different from a multi-class problem. For a multi-class problem, you need a model selects one class among 3 or 4 possible classes or more possible classes. In a multi-label problem, we have several labels associated with one instance, right? In this case, the query by committee is a very appropriate strategy for selecting the most useful instances, because because there is no we cannot choose between the probabilities. We don't have a highest probability for one class. It's just what we get is the probability of that class being present or not present. We are going to see an example in a minute. But then for the query by committee for the multi-class problem, what we do is for each model, we predict class of the classes for each unlabeled example from the pool. And then we calculate the probability of examples belonging to a given class based on the number of votes. And then we select the instances with the uncertain classes, right? After selecting these instances with the uncertain classes, we present them to the human or the user for annotation. And then again, these newly labeled data, they are sent to the model again, and then the model is retrained. So I'm going to show you here an example code. I think it's going to be more clear here. So for instance, we have 4 models here. So then in model 1, we have, for example 1, we have these predictions: 1100, model 2, 1011, 30010, and so on. For example 2, we have these other 4 predictions for example 2. And then what we do is we calculate the probability over the predicted classes. So then, for example, in this case, for example 1, we get a probability of 0.5 because for 2 models, the labels for 2 models, the first labels are present. This is present, but for model 3 and 4, the first label is not present. So then the probability is 50%. For the label number 2, there just one model predicted that label present. So then the probability is 0.25. In the third, the probability is high because 3 models predicted that label is present. So then the probability is 0.5. In the fourth case, we see that all the models predicted that the last label is not present. So then we get the probabilities associated with each of the models here, okay? Associated with the ensemble of models. After that, we can get an entropy score, as I said, as I showed before, right? But in some cases, you just don't need to calculate the entropy score. we just get the probability, and then we just need to select the instances with the highest number of the highest number of probabilities that are 50%, because 50% is very close to a decision boundary, right? So then that could be the chances of being present in one class is 50%, as in these examples here, examples 2 and example 1 for the first label, and then example 2 for the third and fourth label. Okay, does that make sense? Okay. So another way is to calculate the agreement, as I said, using an agreement measure. So for each model, we predict class of each unlabeled example from the pool, as I showed, and then we calculate the agreement between the models using the Krippendorf alpha score, or it could be also Cohen kappa. And then we rank order the pool from the lowest to the highest agreement scores. And after having this pool of unlabeled data rank ordered by agreement, we then present for human annotation the scores with the lowest agreement, right? Because the scores with the highest agreement, we assume that they are not so informative. And then after that, we retrain the model. Okay, so then let's say here, this is an example very similar to the previous one as I showed, but without calculating the entropy. Calculating the entropy is optional in this case. And then, as I said here, we present the example first for model retraining, because here there are two classes with 50% probability, and here there is just one class with 50% probability. Now I'm going to show you using the kappa scores. So let's say we have 3 models here, and then we have the prediction for example 1, example 2, and example 3, right? The predictions for example 3. And then for model 2, for model 3. So then what we do is that we compare. We compare the agreement for each model for number 1, number 1, number 1 here. And then number 2, number 2, number 2, and then number 3, number 3, number 3. What we get here is an agreement score, or a Krippendorf coefficient score associated with example number 1. Another another score associated with instance number 2 or example number 2, and another agreement score associated with example number 3. So then when we sort, we can see that number 1, example number 1, is the one with the lowest agreement score between the models, the 3 models. Number 2 is the second lowest, instance number 3 or example number 3 is the second lowest agreement score, and example number 2 is the highest agreement score between the models. Does that make sense? Okay, so now I'm going to show you, before the quiz, I'm going to show you how to code this. Like, I'm going to show you Google Colab notebook with the code for all of these strategies. So then we can have a better idea of how everything works in practice. Okay, just a moment. I'm going to stop sharing here. I'm going to reshare my screen. Just a moment. Okay, so then I'm going to send you, I can send you here in the chat. I'm going to put here in the chat for everyone the notebook, the link for the notebook, so then you can also run from your computer if you wish to. Just a moment.
Perhaps you can share it maybe later after the class in the activity feed.
Okay, yeah, I can share later one. Yeah. Okay. So for the least confidence, right? The normalized least confidence. As I showed, we can normalize the least confidence using that formula that I showed you. So for instance, we have here the predictions associated with instance number 1, predictions associated with instance number 2, until number 5 predictions. And then I have here a function to calculate the normalized least confidence. We subtract 100% confidence from the maximum probability, and then here we normalize, right? B and D are the normalization. And then we get here the scores, right? And after that, of course, we can rank these scores in descending order. For margin of confidence, same here, we have predictions associated with 5 different examples. And then what we do is we subtract one from another. Right? So the most, so then first we need to sort the instances, because we need the highest, the scores with the highest probability first, and the second highest probability in the second place. And then we subtract the first one from the second one, right? And then what we can do is 1 minus this product, and then we get the scores here. Is that okay in terms of code? For racial confidence is the same. We just divide the second most probable with the highest probability from the first one, and then we get the scores here, and then of course later on you can sort. And the code for the entropy, we have here the instances associated, predictions associated, probabilities associated with the instances, different instances here, instance for example 400, 401, and 402. And then we have to upload this module here for us to calculate the logarithm base 2, and then we calculate the probability multiplied by the log 2 of the probability, and then after that we sum all the entropy scores, and then we subtract from 0. So in the slides you can find the formula here, and then this is the code associated with the entropy here. Okay, this is rank ordered here. So then the instance number 402 is the one with the highest entropy score, right? So then this is the sorted discourse. So then if we need to present to a human for evaluation, or for annotation, sorry, so then the instance number 402 would be the first one, followed by instance 400 and 401, okay? For agreement, the code for agreement score, and then for multiple models. Here we have the predictions for 3 models, right? So then you calculate the agreement using the Krippendorff alpha for all the instances from the 3 models. So then, for instance, we have agreement for instance number 1, for model number 1, the agreement for each of the instances between the 3 models, right? And then here, if we run this code here, I mean, this is because we need to install first the module. Then we get also scores, the agreement scores associated with the 3 instances. So then instance number 1 is the instance with the lower agreement between the 3 models. Instance number 2 is the second instance with the lowest agreement. And instance number 3 is the second one with the lowest agreement, and instance number 2 is the third one with the lowest agreement. Okay, so then instance number 1 would be the first one to be presented for a human for annotation. Okay. Any question here in the code? No? Okay, in the next session number 3, we will have the chance, we are going to have the chance to work on a real world use case for NLP. And then we'll have the chance to compare all of these strategies and see which one is the best for our use case. Okay?
Sorry, Natalia, should we have something installed then for next week?
No, because I'm going to provide the notebook with all the modules that needs to be installed, and then we are going to use a Colab notebook.
Okay, thanks. Yeah.
Okay, that I'm going to provide to you.
Lovely, thank you.
Okay. So no questions so far? Okay. So now it's our quiz time. And after that, we are going to finish this session. So share again. So let's see what we have learned so far. So let's see, which technique takes the difference between 100% confidence and the most confidentially predicted label? Entropy sampling, ratio sampling, or margin confidence? What do you think? The difference. So the difference is margin confidence. Yes, that's correct. Yeah. For probabilistic models, the best technique is entropy sampling, query by committee, least confidence, or none of the above. What do you think? Only two people responded so far. Only 2. Actually, the answer is letter D, none of the above, because for probabilistic models, we can use we can use all of these strategies, right? Entropy sampling. We can use also query by committee. Remember that we can average the probabilities from an ensemble of models. And we can also use least confidence, which is using the normalized least confidence. So then for probabilistic models, this is, we can use all of these strategies. Okay, does that make sense for you? Okay, yeah, this one was the tricky one. Okay. Query by committee is a strategy that involves a single model, multiple models, or only two models. This is very easy. Multiple models, yes. But don't forget that we can use a single model, right? We can use a single model because we can run several, we can do several runs of the same model, and then we can use, we can calculate the agreement between the predictions of these several runs, right? We can also use only two models and calculate the agreement between only two models, right? Query by committee is a good strategy when you have multi-label classification problem, binary classification problem, multi-class classification problem. Yeah, query by committee is a very good one, as I mentioned, when we have a multi-label classification problem, right? Although query by committee can also be used by binary classification or multi-class classification, as I said. But for multi-label, it's a very good one because when we have a multi-label classification problem, we don't have different probabilities or options for one label. Usually what we get is a sequence of labels, predicted labels, which the model predicts whether it is present or not present, right? So then the query by committee is a very good strategy when we have an ensemble of models, and then we can calculate the probability based on the final predictions of this ensemble of models, as I showed before. Right? Does that make sense? Okay.